Morning, everyone.
Hello.
I think we have a test on Wednesday, is that right?
Yes.
Okay. I don't like it any more than you guys. I have to write the test, I have to grade the test. I wish I could just take the test. But actually, it's something to be excited about, right? Ultimately, it's a positive thing, right? Chance to demonstrate your knowledge. So let's just spend today reviewing for the exam primarily.
Oh, yeah.
I put a bunch of practice exams on the class webpage. Have you guys been looking at those exams? So why don't we go through them and I'll just take questions like, why don't y'all just look at those practice exams and challenge me to see if I can solve them. Or we can talk about anything y'all want to talk about. This is like this more of a discussion where you guys tell me what you want to study, right? What you need. Yes.
Can you talk about ruled surfaces and rulings and how you can have tandem vectors? I saw it in one of the midterm.
Was it on one of the midterms?
Yeah. That was confusing.
So, ruled surfaces, right? We can call them popsicle stick. Is this how you spell it? Popsicle? No. Is that right?
I think so. Yeah,
Popsicle stick surfaces, right? I mean, and they're about as important as actual popsicle stick suggests, okay? It's not that important. It's just an example of a kind of surface. It's kind of cool. It's kind of cool. Like the helicoid is a ruled surface, I think. Isn't that true?
Yep. Yeah.
All right. And that one is more obvious that it's a ruled surface. Now, what is a ruled surface? It's made up of popsicle sticks or lines, right? Okay, that's pretty cool, right? So it's a union of an infinite number of lines, right? Okay, cool. All right. Some of them are kind of surprising. Like, isn't like some sort of hyperboloid actually a ruled surface or something like that? And that one is not so obvious, right? So sometimes every once in a while there's like a ruled surface. You're like, really? It's a ruled surface? It's like, oh, okay, cool. Okay, so what? I'm trying to remember how this goes, but one thing is nice when you ask me questions like this, you get to see me think. Okay, it's like okay, so I know there's two parameters u and v, and so I have to, I have to equal x comma y comma z, right? So I'm gonna have I forget what the book does, but one parameter will be the parameter along the line, and the other parameter will be the parameter for the curve. So now, what is the equation of a line, right? The equation of a line is some p, let me leave a gap there, plus, let's say, v times q. You guys agree? Because that's the equation of a line. You start at the point p. When v is 0, right? Then we get the point p. When v is 1, we get p plus q. When v is 2, we get p plus 2q, right? This is the equation of a line. Did I do this right?
Mm-hmm.
So that's one line, okay? But what we want is, we want u to parameterize all the lines, right? And so for each value of u, we want to get different lines. So the point is this p is a function of u, and this q is a function of u. And so I think that's what a ruled surface is. I don't have that memorized, by the way. I just figured it out. Now in the book, they might have had the u and the v switched. Do they or don't they? Is this how they did it in the book?
Yeah, I think so.
Okay, well, it's 50-50. I had a chance. But both of them would be ruled surfaces, just which parameter is for the parameterizing which line, u in this case, and which parameter is the parameter of the line, right? So that's a ruled surface, and then you can, it's just an example of surfaces. Do you have anything more specific than that? Does that help? I mean, that's how I think of it. Now, is there a problem you want me to work, a specific one?
Yeah, it was one of the midterms. So basically,
Which, if you could tell me what year it is,
okay.
I can pull up on my phone.
There were some proofs associated with doubling and triply ruled surfaces.
Okay, now here's, let's talk about in general, what can we say? One thing we can say, and this is our general understanding, right? Y'all remember that, by the way, I have not written your exam yet. And And I never do. I always write the night before. And the reason is that today I am on your side. I am trying to help you predict what will be on the exam. I'm not keeping any secrets.
We're telling you what we don't know.
That is true, but I have no desire to make it. I don't want to trip anyone up. I actually want everyone. I want you guys to learn, and everyone gets an A+ in the class. That would be the ideal. Wouldn't that be the ideal? Okay, that'd be my first choice. But seriously, I don't know what's on the test, so I will tell you everything. I'm an open book. Okay. You can ask me, might that be on the test, and I'll tell you what the percentage odds are and all kinds of stuff. But if we look at what normal curvature is, or I like to think of as cross-sectional curvature, but they call it normal curvature, right? It's K of U is equal to U dot product S of U, right? Is that right? I think so, right? And then, but the point is this little, we have a capital U here, right? And then a little u here. And so this little u is what's going around. And of course the shape operator is defined in terms of capital U. But the point is this equals the cross-sectional curvature, right? There was some formula we have in the book. What does it equal? It equals alpha double prime, no, beta double prime of S, right? So if it's parameterized by arc length, right? Dot U, is that right? Or is it the negative of that? That's a big U here. Is this correct, or is it my alpha last time? Is this correct? I think this is correct.
I think it's B double S 0 or something like that.
Beta double prime is 0, yeah. Where if you look at the plane defined by these two U's, you get this curve here, right? And if we call this curve beta of S, then the point is, and this right here is S equal to 0, right? That's beta of 0 at that point, right? Mm-hmm. Then this is simply the curvature in that plane, right? At that point. So this normal curvature is really cross-sectional curvature of that curve, right? Because we know this beta double prime is perpendicular to the curve, and so it's either going in the direction of u or perpendicular to the u. So this is up to a sign the absolute value of beta double prime is 0, which is what we call kappa, and then it's negative if it's curving away from u, and it's positive if it's curving towards u. So it's a signed curvature. And furthermore, we know that K1 and K2 can be expressed in terms of this normal curvature. K1 is, I like to call it the min, and K2 is the max. I forget what the book does. Do they do the opposite, or do they do that?
They do the opposite.
They actually do the opposite? Mm-hmm. It's just funny, right? Okay. Anyway, whatever. K1 and K2 collectively are the mins and maxes, right? Did they actually do this as the other way around? Mm-hmm. Okay, I'll follow the book. I'll follow the book. Even though 2 is bigger than 1.
First place is better than second
Don't. I don't even want to think what you're trying. Because you're trying to justify something I don't even want to think about, right? Because like, I can play along. It's just a funny thing. I never would have questioned it if a professor at MIT hadn't pointed out the most reasonable conventions. 1's less than 2, so the min should be the 1 and the max should be the 2. And then once you see that, you can't unthink it for me, you know. But okay, I'll play along. Whatever the book wants to do. Anyway, K1 and K2 are the min, the max. And so, but wait a second. We already know there's one value of u where the cross-sectional curvature is 0, don't we, on a ruled surface. Is that fair? Like, what do we know? On a ruled surface, it's made up of lines, so that means if I choose some direction, then the direction of the line, right? Where this value is going to be 0, right? Because this right here is 0, right? Mm-hmm. And so with a ruled surface, we immediately know that that if you have K1, K1 is the max, okay. So K2, 0, and K1, right? Like this, right? So we know that One of them is bigger than 0, and one of them is smaller than 0. And really, that's the main thing we get from being a ruled surface that I remember. And so in particular, now, do we know what the sign of the mean curvature is? No, because I don't know if the sum here is going to be bigger than 0 or smaller than 0. It could be either, right? But what do we know? There's another curvature quantity that we do know that's signed.
Gauss.
Gauss curvature, and why is that?
Because it should be 0, because in one direction it's just like a plane, basically.
Well, what we know is that Gauss curvature, right, is the product of these two guys, right? And they have opposite signs, so therefore this is less than or equal to 0.
Oh.
Yeah.
Why wouldn't it just be equal to 0? Because there's a line in one direction at every point.
Oh, it's because K1 and K2 are the mins and maxes of this. Yeah. So it could be that 0 cross-sectional curvature isn't an eigen direction necessarily. It could be. Right? It could be 0. But K is just the product of the min and max of the cross-sectional curvature or normal curvature. And so we just know that 1 is bigger than 0 and 1 is less than 0. If either of them is 0, then sure, this is 0. But one could be -5, the other could be +3, right? In which case, the Gauss curvature would be -15. Okay, so we know that the Gauss curvature, we know it's a non-positively curved space. Some people would say it's a negatively curved space, but 0 is not negative. So technically it's a non-positively curved space. Okay. Okay, that could be a problem. Is that what the problem was? Prove the Gauss curvature is less than or equal to 0 or something like that?
Something like that, but it also had doubly and triply ruled surfaces and how these things happen. Like
Oh, the problem had doubly and triply.
Yeah, triply ruled surfaces.
I don't even remember. What is a doubly ruled surface? I don't even remember. I wrote the problem, so my test?
Yeah, 2016 problem 5.
Okay.
It's like there's 2 different Q or something that satisfy the equation.
Oh, it's 2 different ways to rule it?
It's like the hyperboloid is doubly ruled because you can do it this way. Like
Oh, okay. It's 2 different ways to rule it. Okay.
Yeah.
And so what was the point of the problem? By the way, I have solutions on the internet too, right? So you can just read me the answer, right? So
Yes,
what?
I could not completely understand the solution, that's why.
Okay. What does it say there? Can you just read out the answer? Or what was the question, first of all?
2016 problem 5.
Okay, let me get to there.
Almost got it, but
2016.
problem
Whoops, not the final exam. We're talking about midterm, right?
midterm, yeah.
2016 solutions. Problem 5. This was an interesting problem, wasn't it? Is everybody looking at 2016 number 5? Different rulings are required to have different directions. Oh, okay. Okay, I'm trying to remember. Okay, so part B is what we just did, right? Part C now.
Which problem is
2016 question 5.
it? Okay.
Okay. This was a thinking problem for sure. Okay, so let's see here. Theta. Yeah, okay. I like it. I think what's really weird is when you get older and then you read a paper you wrote 20 years ago and you're like, has your name on it, right? And you're like trying to understand your own paper, right? It's like, okay, and it's just like you remember it in your brain, like, oh, this was easy, right? And then you start to read your own paper, and you're like, what's going on here? I remember the basic idea of this problem. Let me tell you what the basic idea is. The basic fact of this is testing is that, and we did this in class, is that when we look at this U here, right, this U can spin around this way, right? And when you look at these, the mins and the maxes, this is actually achieved. This is actually K of U2, right? Achieves the min, and then K of U1 achieves the max. And what we know is that if these are actually the eigenvalues of the shape operator, right? And eigenvalues, when they're distinct, it means the eigenvectors are perpendicular, right? We went through that, so you can review that argument. It's linear algebra. And even if the eigenvalues aren't distinct, that means if there was K1 equals K2, that means the shape operator is just a multiple of the identity. It means all vectors are eigenvectors. And so without loss of generality, I can choose U1 and U2 to be perpendicular. Okay? Okay. Which means I can consider all possible U. Let's say U of theta in the following way. This is cosine theta times U1 plus sine theta times U2. And those are all possible unit vectors. We'll take U1 and U2. So when I follow cosine theta, I think I use V1, V2 in my answer here, but it doesn't matter. They're the principal curvature directions. And so then when you say, well, what is K of theta? We can just define this to be K of U of theta, right? And so this is U of theta dot product the shape operator of U of theta. And so I work it out in the notes there. And I'll just skip one step. This is K1 cosine squared theta plus K2 sine squared theta, which we did in class. And this is kind of nice because, like sine squared plus cosine squared equals 1, right? And so, and they're both positive. So what this allows you to see is why K1 and K2 are the mins and the maxes, right? Because when sine theta is 1 and sine squared is 1 and cosine squared is 0, then you just get K2, right? But when cosine squared is 1 and sine squared is 0, then you get K1, right? So the extremal values, right, goes between K1 and K2, right? And if you were to graph that, what it's going to look like then is just a sine wave like this, okay? It's periodic. Now you might say, wait a second, but that's a sine wave squared. But if you mess around with sines and cosines very much, you know that when you multiply cosines and sines, you get sums of cosines and sines. And that comes from these summation formulas. Do you guys see all that trick? When you multiply cosines, sine wave. When you multiply sine waves, shifted and all kinds of stuff, you get sums of other sine waves, not just, it's a very interesting fact. And so sine waves squared look like shifted sine waves. Ask me after class if you haven't seen that. And let's see here. So this right here would be a minimum. This is let's see here. So for example, that might be 30 degrees. Now we know that the period of this, when you square a sine wave or a cosine wave, it halves the period. So the period is actually 180 degrees. So this would be like 30 degrees plus 180 degrees between the mins. As an example. By the way, to make that more precise, and I do it in there, you can use your half angle formulas, and this is K1 times cosine squared is 1. Is it minus cosine 2 theta over 2?
Yes.
I think it's plus.
Oh, it's plus? Yeah, okay. easily checked. And then K2 is 1 minus cosine 2 theta, right? Over 2. And that allows you to see that actually it's the sum of sine waves, right? Okay, and with period 180 degrees. Okay, but in our case, we know that the graph doesn't look like that because we know there's at least one value where K of theta is 0, right? So we're trying to come up with, what does our picture actually look like? So it's got to be shifted down to actually intersect 0, right? And so maybe it might look like this or something. Okay, and so then the minimum is happening here, the maximum is happening there, and then there's your 0. Okay. And now, is it the only 0? So by the way, this right here, this increase here is 90 degrees, right? The periodicity is 180 degrees, right? So then this would be another 90 right here, right? 180 degrees for one period. But it's 90 degrees between min and max because they're perpendicular, right? And then there's your 0, which is neither a min nor a max here. Now, to be doubly ruled, right? There's got to be two different directions
With 0, yeah.
with 0. And so, I'm a little bit confused here. I have to admit. What am I confused by? There's your other 0, right? Wait a second. Yeah. Okay, got it. And that's a different 0 because see, this 0 here is the same as that 0 there. That's 180 degrees later on. Okay, so this is a different 0. You can have a doubly ruled surface. In fact, whenever you have in this picture, you can see generically when you've got one 0 here, then you get another 0 there, right? So we could call this the min is what they call theta 2 because 2 is less than 1, right? And then the max, that's theta 1 because 1 is bigger than 2. Okay, and that's 90 degrees, right? Okay, and so the period here is 180 degrees. So this 0 here is the same as that 0 there, right? See how it's coming from the min up, right? So this right here would not be a different point. That's just off by 180 degrees, right? It's the same rule, right? But that's a different 0. Okay, and you get a different 0 generically. If you have one 0, then you get another 0. There's only one time when you don't get a different 0, and that is we can't let this gap here be 180 degrees because then they'd be the same 0, right? We can't let this 0 and this 0 be the same, right? And that happens when it shifts and it just barely touches, right? And then that would only be singly ruled, and that's when the minimum. So the point is you can't have this thing just going down and just barely touching. Okay, that's the way to understand the picture of it. Okay. Now, what did I write? I forget exactly, but it's probably some mathematical way to explain that. Or maybe I just did it with the picture there, right? Yeah, so it's understanding that with this picture that to get two distinct places where this K of theta is 0, we need the minimum to be strictly negative. We also need the maximum to be strictly positive. Because otherwise, we would have
Singly ruled.
it would only be singly ruled.
Okay.
Right. The zeros would differ by exactly 180 degrees, which is the same eigendirection, right? a direction and go 180 degrees, just pointing exactly the opposite direction, which counts as the same direction for eigenvectors. Now, the last question is, what about triply ruled? How in other words, in 180 degrees, let's say, from minimum to minimum, right? How could you have 3 zeros, and you just look at it, and you use the argument, any fool can see that a sine wave cannot intersect 3 times, right? In one period, unless it's the 0 sine wave that intersects an infinite number of times, right? So if you're triply ruled, then it must be that that K1 and K2 are both 0. Yes?
Can be an example of a triply ruled surface, a plane?
The plane. Yeah, that's the only one I could think of. And we know that K1 has to equal K2 everywhere, which means the shape operator is 0, which means it's a plane. Yeah. Did I ask you to prove it's a plane, or I think I just said
No.
prove it?
Yeah.
K1, K2 are both 0. Okay, so that was a clever one. It's number 5. Let's see, is that the 5th of 5 problems, or 5th of 6 problems? 5th of 6 problems. I don't always, it's supposed to be an increasing order of difficulty roughly, but not always exactly, because so don't get stuck on a problem. Like that one was a little bit clever, right? On the other hand, it's just realizing that this K of theta thing is of this form, right? And then use the picture. Yes?
Why is the min and max perpendicular at all times?
Oh, that's just the fact that for a symmetric matrix, eigenvectors are perpendicular, right? Actually, there's a couple ways we could prove this, okay? So first of all, there's a linear algebra fact that when you have a symmetric matrix, the eigen vectors are perpendicular.
Okay.
All right, so you can look that up. Why is that? Well, let me not repeat that just right this second. Let me use the equation that's on the board. And once we realize, okay, no, I really can't. I'll be assuming what I want to do. Okay, so
Because I can think of a counterexample, if you can disprove that. It's like like the bottom of a Coke bottle.
Yep.
If you could imagine, just
Like
4 mountains.
a can
together.
or a bottle or
A
what?
bottle. So wait, there's
Okay.
a bottle right there.
Where? Oh, okay.
Yes.
Okay.
Look at the bottom.
Yep.
So like the bulges are like where K is max, and the into is where K is min,
Mm-hmm.
and they obviously isn't at 90 degrees.
So you're talking about at this point here?
Yes.
Okay.
I'm taking the middle of the bottom as like the
Here?
yes.
Right
as
here?
This is the origin, or like yeah.
Right here?
Yeah. This
So that's
is,
the,
this
by the way,
is
that's
the
wait a
this
second,
point.
that's just the top of a sphere, right?
Yeah, but then there are like little things on the side that's not fully going in or going out.
I mean, you have to. Everything we do is for a smooth surface. Okay, so
Okay.
you're not talking about the irregularities here, right?
Okay.
It has to be smooth.
Also,
So-
this angle that we're talking about isn't between different points on the surface. It's for a single point, like looking at how its curvature changes if you change your direction.
Yeah,
how you're
so
going.
if you change the direction of the bottom point, when it's at like a bulge, it's going to be maximum, and when it's at like a into, I don't even know what.
Are you talking about these dimples here?
Yes, okay, thank you, dimples, good word
Okay.
to use.
Yeah. Okay. So this, first of all, even on this bottle, the dimples do not extend to the origin here.
Okay.
Okay. So the point is that's irrelevant for computing the tangent plane here. Now you might say, well, I could have made it. Well, if you did, it wouldn't be smooth. Yeah. So I think
So-
you're okay. So you have a counterexample, but this is a surface that's not smooth, right? So the point is that when you assume that your surface is smooth, then the essentially what it comes down to is that everything, if you look at it as a graph, z equals a constant plus another constant x squared plus another constant y squared locally models things up to translation and rotation, right? And that's a smoothness argument that's the case. Okay. So how about this? I'll even okay. How about this? I'll prove it algebraically if you don't believe the linear algebra proof. Okay. But this uses smoothness. suppose something is of the form a plus bx plus cy plus d x squared plus exy plus fy squared, okay? And then plus order, plus cubic terms, okay? I've got all the 0th order, 1st order, and 2nd order terms, right? Okay. Then you can now suppose that the gradient is 0. So we want it to be, let's make the tangent plane is flat, right? Tangent plane flat. That implies that b equals c equals 0, right? So in other words, we're looking at the graph of this, and I want the tangent plane to be the xy plane, right? So we have some curve here, right? Some surface, right? If you want the tangent plane to be the xy plane, then b and c must be 0, right? Okay, so they're gone. And then it turns out that you can rotate this thing, right? I can rotate this picture. That's 1 degree of freedom, right? And with that 1 degree of freedom, I can make e equal to 0. And so then you get z equals, a plus, if you like, d tilde x squared plus f tilde y squared. Okay? And you can always get that e term to go to 0 by rotating in the xy plane. Okay? Now I'll leave that as an exercise for you if you want to play around with that. Okay? But it should be believable because I have 1 degree of freedom, rotation, and I'm saying I have to get one thing to go to 0, right? If I rotate it, e is going to change, and it turns out I can make e positive or negative, and in fact I can make it 0. Right? I'll just state that as a fact. Should be a believable fact. Does that sound believable? We vote on it. Make see if it's true or not. It's not how we. No, it's true. Okay, trust me. Okay, but that should be believable. And then you can have this form, and then what you can see is that we have 2 curvature directions: one the x-axis, one the y-axis. And these are your, up to a factor of 2. These are your principal curvatures, d tilde and f tilde, and they're in perpendicular directions: one in the x direction, one in the y direction. Okay. They could both be positive, both be negative. One could be 0, one could, so this is, now, but here's my point. We had to assume their original thing was smooth for this argument to work. Right? We're assuming that you can approximate it with this up to 2nd order. So if you take something kind of crazy, for example, what you're kind of doing is, let's take a really curvy curve, right? Like this. Let's pick a point, and then let's look at the cone over that point, right? Well, yeah, and then you get all kinds of crazy behavior over that cone. It's actually not smooth at this point, right? And when you look at cross-sectional curvature, it's going to be extremely complicated, and it's not going to be of these forms. Right? Everything here is assuming there'll be a smoothness at that point. And so when you look at this bottle, which, you're kind of taking, you're doing something. So you're saying, oh, look at this complicated curve, this irregular thing, right? And you're extending it all the way to the center of the bottle here at the bottom, right? You're doing something, you're smoothing it out a little bit, like you're rounding it, whatever, right? But it's essentially the same issue, is that you're not getting the required regularity that we're assuming in all of our calculations. Yeah.
Thank you.
Because otherwise what you're saying is true. Why couldn't we have any cross-sectional curvature we want in any direction at any time, right? I mean, why not, and that's good to understand, like, why not, if you have some surface here, right, so some lumpy potato, right, and you look at the cross-section, why can't I just define my potato to have whatever weird cross-section I want at each point, right? In which case, the cross-sectional curvatures could be whatever I want as a function of theta, right? And the point is you can do that, but it's not going to be smooth at this point. It's a great question, actually. It causes us to probe deeper. In the 1800s, if not earlier, the old-fashioned way of looking at smoothness of things was that anything worth studying was smooth. That nature was smooth. It was natural. It was virtuous, perhaps, right? And that things that aren't smooth, well, that's not natural. Like, that doesn't happen in nature. Why would you want to think about that? Okay, that was kind of the attitude, and I think maybe we have that attitude a little bit too every once in a while, right? But that's not the current modern attitude. The modern attitude is no, some things aren't smooth. You can take some weird cone or something, right? And you just need to recognize we're making an assumption. Things are smooth. And in fact, there are some things that are very important which aren't smooth. Things that jump to my mind would be the Big Bang or singularities inside black holes, right? Are singularities, and so that's nature, or at least that's part of a great theory, great theories. The other thing I'll share with y'all, just real quick, and then we'll do another problem, is if something called the Simon's cone. I think I mentioned this in my office hours. Simon's cone. Let me tell you what that is. That's x1 squared plus x2 squared plus x3 squared. This is all happening inside of 8-dimensional space. Plus x4 squared equals x5 squared plus x6 squared plus x7 squared plus x8 squared. So look at the set of points in R8 that satisfy that. That's a cone. Why is it a cone? Because if the point x1, x2, x3, x4 all the way to x8 is in there, then if I multiply it by 10, it's still in there, right? Because this would scale by a factor of 100. If I replace all the x's by 10 times those x's, it's still an equation. So the Simon's cone is some sort of cone, right? Let me just try to draw what it looks like. First of all, how do we visualize 8-dimensional space? Well, that's S7 sitting inside of R8. I've obviously drawn it as a 2-dimensional sphere sitting inside of R3, right? But this is the best we can do. And then there's going to be some sort of cone here, right? So I'm just going to draw some surface here and then just pretend like this is the correct surface. Y'all see the cone I've drawn in there?
Sure.
Okay. That represents the Simon's cone. So it's like a 7-dimensional cone. It's codimension 1, just like the sphere. And here's what's kind of cool about it. It's a minimal surface. It actually has zero main curvature everywhere. And but then you have this singular point at the middle, which was this cone point, right? And you're like, oh, that's not natural. You can't talk about what H is there. But here's what's crazy. If you fix this cone on the spherical boundary, if you say, okay, fix it where it intersects that sphere, for example, and then say fill in with the surface, the codimension 1 surface, with that has minimal volume, surface area, but generalized to higher dimension. It's that. This thing minimizes surface area for its boundary. And it has a singularity. And this is the first example where a hypersurface that minimizes area has a singularity. So this singularity is very natural. There's literally a minimal. You think it's a soap film. That is a soap film. Like if you were in 8-dimensional space, it would be like, okay, we live in 3-dimensional space, but if you lived in 8-dimensional space, there would be a wire frame you could stick into a bucket and pull out, and there would be a cone there when you pulled out the soap film. Isn't that crazy?
It's pretty crazy.
Yeah. And it doesn't happen until you get to dimension 8. Does it? Yeah. So, yeah. And by the way, this is actually not irrelevant. We use minimal surfaces to prove things in mathematics, and the positive mass theorem is, why when you jump up you come down. This positive mass theorem is not known in higher dimensions because of this problem right here. It's kind of quite annoying.
Okay, wait, sorry, back to the final. So
Yeah.
I'm wondering, is there a way, there seem to be a few types of questions that are a little bit more abstract. They're like, they give you an equation of maybe a patch or a parametrization. They say, what surface is this? And if it's like not immediately obvious what it is, like what's your process to figure out like intuitively what the surface represents?
Okay, so if you're talking about questions I've asked or the book has asked?
That you've asked.
Okay, so there's only a few things I expect you to know. For example, if you compute the shape operator and it comes out 0 everywhere, then I expect you to know that that's a plane, right? If you compute the shape operator and it's a multiple of the, let's see here, the shape operator, let's say that the principal curvatures are constants, right? K1 equals K2, and they're the same everywhere, right? What's that?
It's a sphere.
It's a sphere, right?
Or a plane.
Or a plane, thank you. in case they're both 0. By the way, which is just a very large sphere. Let's just be, right? A very large sphere with center infinitely far away, right, is a plane, right?
Well,
Okay, sort of.
I don't like thinking about
Sort of.
that.
It's certainly the limit of plane of spheres. The limit of spheres is a plane, right? So it should be in the same category of things, right? So it's not really it's a second case, but it's really the same. You know, it sort of fits nicely, right? Okay. Cylinder. You know, again, I mean, so there should be things like a cylinder. You know, you recognize some basic shapes, right? I would not expect you to identify some bizarre shape, right?
Okay.
Like. So hopefully the questions that you're pointing out were reasonable cases where, yeah, I could get that one.
They were pretty
Okay, yeah. Other questions? Yes.
Can we like briefly discuss the shape operator and how it's related to like eigenvalues and eigenvectors again, and then what sorts of stuff we might need to know about that?
Yeah, I mean, just that it's this thing here, right? And so I guess to sort of complement this discussion, it's that the shape operator. First of all, it's defined to be the well, I guess we could put a V there, right? Is the negative covariant derivative of that unit normal U here. It's this big U here, right? And that's given at any given point P. You want to know the definition of the shape operator, and then also you'll want to know that that's symmetric. Okay, so everyone should know that's symmetric. What does that mean? It means that V dot the shape operator of W is equal to W dot the shape operator of V. And then from that, we were able to show that if you choose any orthonormal basis, then the representation of the shape operator will be symmetric. So in other words, A, B, C, C. Okay, so any orthonormal basis, then what that gives us then is when we use that matrix to represent the shape operator, right? Now, what does this mean? It means an orthonormal basis, we could call it V1 and V2, right? Then when you plug in, what does this mean? It means the shape operator of V1, which you think is 1, 0 is equal to, A V1 plus C V2, right? And the shape operator of V2 is equal to C V1 plus B V2, right? That's what that means, right? And then we're like, okay, but that's a symmetric matrix. Then this has orthogonal eigenvalues. Okay. And so this is all explained in the book. Let me not repeat then everything, all right? But the end of the story is that you get eigen vectors and eigenvalues. So the shape operator of U1, which is an eigendirection, it's an eigenvector of the shape operator, is equal to K1 U1. And the shape operator of U2 is equal to K2 U2. And so with respect to this basis, U1, U2, which is also orthonormal, then the matrix A we get representing the shape operator is just K1, K2, and then zeros on the off diagonal. And so then when you say, well, what's the determinant? It was K1 times K2, right? What's the trace? K1 plus K2. And by the way, that's invariant. We use different bases, right? Even if they're not even an orthonormal basis, we showed that the determinant and the trace of these matrices is always the same. So when you change the basis vectors, doesn't change the determinant and the trace. Yes?
When we proved the fact that the shape operator is a linear transformation from the tangent plane to the tangent plane,
Mm-hmm.
we just take a directional derivative with respect to any v vector and
Mhm.
basically use the trig u dot u equals to 1.
Yep.
And so that SPV is perpendicular to u.
Yep.
So how do we know that v initially is in the tangent plane? Because we took
By assumption, it has to be. Yeah, the shape operator here is only defined for v that are in the tangent plane.
Okay.
Otherwise, it wouldn't make any sense.
So that's
Yeah.
Let's assume
Yeah, absolutely. I mean, it literally does not make sense if V is not a tangent vector.
that.
In fact, just just to go over that point in a little more detail.
Because the math works out even if V is not in the tangent plane.
Sort of. I'm going to sort of agree with you, okay? But here's the problem. And there's a sense in which the math works out. Yes. Because you define your U to be this thing, right? And remember how you define the covariant derivative, you just take the derivative of each of the components of U. U is U1, comma U2, comma U3, right? And then we take the directional derivatives of each of the components. And so your point is that U dot U is equal to 1, right? And so if I take the derivative in the V direction, right? Then I get 0 here, and I get twice U dot product the shape operator in the V direction of U, right? And so that means that the shape operator VU is perpendicular to U. This only uses the fact that U dot U equals 1 everywhere, right? And so here's the technical point. Say we're doing it at this point here. There's your tangent plane, right? Technically, when you go off the surface over here, see how the surface is curving away? So U's not even defined on that plane, technically, right? So why does this make sense anywhere at all? Right? Because U's only defined, at first anyway, on this potato, right? It's on the surface of the potato, right? It's not defined everywhere in three-dimensional space. So I did mention there was a technical point at the time, but I didn't get into it, right? And so the technical point is that to actually do this, the trick you do is you say, well, suppose that everything in the site is smooth. This is a smooth potato. U is smooth on the potato. And then we're going to suppose it's possible. What you do is you extend U smoothly. To say some neighborhood of the surface in R3. You can say to all of R3, doesn't matter, right? And it turns out you can always do that. It's a technical point, we're not going to get into it, right? And then the second point is that you extend it however you want, and then as long as V is a tangent vector, it doesn't matter how you extended it. That's the exercise. You just show, okay, extend it, compute those derivatives, and then show it didn't really matter how you extended it anyway, so, So in some sense, we can't, but by the way, at that point, the fact that it doesn't depend on how you extended it requires V to be a tangent vector. Because if V was, let's say, going off into some direction like this, right? Well, then it does matter how you extend it. Right? Okay. Yes?
Can you just quickly explain again why, when we take the derivative with respect, or in the V direction, why that equals 2U dot the shape operator of U?
Okay, sure. So why is this calculation correct?
Yes.
Okay, so it's, I'll put in more steps. This is, take the directional derivative in the V direction of U dot U, right? Now what is U dot U? U dot U, remember U, that's going to be like, if we say U here is equal to U1, U2, U3, I think that's what the book does. They use a superscript, I think, right? Do they? I think so. Okay. So then you get U1 squared plus U2 squared plus U3 squared. And then you apply your knowledge of calculus to get that this, for each term, right, you're going to get 2 U1 times V of U1. And then plus 2U2 V of U2. Oops, I don't know why I started doing subscripts there, sorry. Plus 2U3 V of U3, right? Did I mess up yet? I think that's right, right? And then you're like, but wait a second. That's just 2U dot product this comma that, which when you stare at it, like, oh, wait a second, that's the definition of the covariant derivative of u. So it all works out by definition, and that means that this dot that must be 0, so they're perpendicular.
Sure. Thank you.
Sure. Other questions?
Are Gauss maps within scope for the exam? And what do they mean? If so.
I think y'all had a homework on the Gauss map, right? So I guess technically, yes.
Yeah.
I don't quite see it being on the exam,
Okay.
but I'm not making any promises. I don't want to go that far, right? The way you have to understand it is the person who's writing the exam is a different person, right? I'm on y'all's side right now, but that person is like, but like my honest feeling right now is that that's like, I like that, but it's for understanding Gauss curvature. And this exam is, that's more like for the Gauss-Bonnet theorem, which we're going to get into in the second half of the course. Maybe for the final exam, that would be I'd be more likely to put it on there. But do I have it on any of the practice exams?
Not that I've
The
seen.
Gauss map? So you're probably okay. But I mean, what is the Gauss map? It's just, it's one of these things that's so simple, it's hard, right?
Yeah.
Right? So it's actually quite simple, but it's the Gauss map G maps M2 to S2, where whatever that normal vector is, right? You translate over here to this sphere, right? And then you map. So if this is the point P, and then that's the vector u, you translate the vector u over here, and then look at where it ends up over here, and then you say the Gauss map of P equals Q, if you like, right? You guys get the idea? So you can think of it, but that Q is really has the same coordinates as u, so Q is u, right? So I mean, it's the Gauss map is u, so the Gauss map algebraically is no different than just the normal vector u, algebraically. Yes?
One thing that I would just like kind of do you expect the Gauss map to be like a function of like path coordinates?
Typically.
X, Y, and Z.
Typically, u and v.
Okay.
Typically. Yeah. Yes?
In the homeworks, we also had something called Gauss map derivative or something like that, G star.
Yeah.
And there was an argument that the range of G star, which is equals to the negative of the shape operator, the range of both of the things are same. And the argument in the book was not very convincing.
The argument that what was the same?
That the range of the induced derivative map of the Gauss map is same as the shape operator.
Okay, so G, so what was it? It was G star, which is pushing tangent vectors, is equal to the negative of the shape operator? Is that what it was?
Yeah.
And that's the thing you didn't find convincing?
No, that was convincing, but
Yep.
there was an argument that the range of the shape operator, which is the tangent plane, is the same as the range of the G star, which is the unit sphere or something. The derivative of the unit sphere or something like that. And there was an argument that the unit sphere basically is the tangent plane or something of that nature. Because if they are equal, then their ranges have to be equal.
How are G stars on the unit sphere?
Well, I mean, G star, right? I mean, it's not going to be on the midterm, so let me go over this pretty quickly because I want to focus on what might be on the midterm. But what is G star? It's vectors. It's basically saying if I go this way, if I'm on look at a tangent plane here. If I go that way, right? What direction do I go over here, right? And well, the directions over here is a tangent plane, right? So so this maps to the tangent plane of the sphere. But the tangent plane of the sphere is also the tangent plane here because they have the same normal vector u.
Okay.
And so that's probably the difference, right? Okay, so the tangent plane, so G star maps to the tangent plane of the sphere. S maps to the tangent plane of your surface. That's and that seems different until you realize that the normal vector here is also, it's the same point here, which means it has the same normal vector, so you can identify them.
Yeah.
Yeah.
Thank you.
Good.
Do we need to know calculus of variations?
No. Oh, wait a second. I mean, okay, I said that too quickly. I don't think I remember putting it on any of the previous practice exams. Is that correct? But yeah, technically we did talk about it, didn't we? Right? So yeah, I don't. The question then becomes, okay, if we discussed it and it's fair game, why haven't I put it on any of the previous exams, right? And I think that's because it just doesn't make a good test question. You know, if I could, I don't want to give you a question that takes 45 minutes, right? That's the problem, right? So calculus of variations is one of the coolest things we've discussed, actually. So yeah, make sure you're familiar with it and understand the basic idea, but the only dangerous thing is you've challenged me now to think of a good calculus of variations problem. But so yeah, make sure you study it, okay? How about that? And know it. And but yeah, why haven't I done it before? I don't think I have, right?
Do you know if
Yeah.
it appears in the book or where?
What's that?
Do you know if it appears in the book or where?
Calculus of variations?
Yeah.
Yeah, it's in that whole variation of area. It's in the book.
Okay.
Yeah. But by the way, I did extend the discussion a bit. I talked about it a little bit more than the book, perhaps. But don't add. I mean, the odds are I won't have a calculus of variations problem like that on there. Odds are. Yes.
And so, in general,
Mhm.
fair midterm topics include all homeworks, including the one due, like.
Yeah. Yeah. All the homeworks we've done up to this point. I think that to be most fair, it's basically the sections of the book that have had homework assigned. So let's just say it should, I think that's only fair, right? Like if I went off on some tangent, that's not fair, right? It's good for your education. I like going off on tangents. Here's something, how we should, like Simon's cone or something like that, okay? You're welcome, all right? But that's not going to be on the test, right? That wouldn't be fair, right? How are you going to study for that? I actually like, as long as you have a good textbook, let's base the test on the textbook, right? Because that way you know what to study. You're responsible for the material in the textbook. Yes?
There are sections of our textbook where we didn't discuss it and we weren't assigned any homework questions. Do we just ignore them? Or
If the section did not have any homework problems assigned, then that means I'm not testing it. I think if you think, that's my intention. Because I sometimes, we don't cover the whole book, right? We cover the sections that I picked out, right? Yes?
Can we run through the intuition on 2017 midterm problem 3?
Okay.
It's about a vector field that consists entirely of umbilic points.
Number 3. Yeah, so that's the proof. That comes straight from the book. Yeah. So that's a proof from the book. It's the proof that if you have an umbilic surface, or if every point on a surface is umbilic, means K1 equals K2 at every point, then it's either a plane or part of a plane or part of a sphere, right? And so, yeah, that problem is just basically guiding you through the proof that's in the book. So let me refer you to the book.
Okay.
And then look it up and study it and learn that, right? And so I gave a sketch of the proof and my answer there. But you might find the book gives more details.
Okay.
Yeah. So by the way, yeah, y'all are responsible for all the proofs that are in the book that I assign homework problems. In any of the sections where I assign homework problems, any proofs in there, you're responsible for those proofs. That's fair, right?
Yeah.
It's a little daunting, right? Because there's a lot of proofs. So remember, you get a review sheet, one piece of paper, front and back. If you want, you could use one side just for like all the proofs in the book that you're not sure you could remember. Right? Just write them out. I mean, it's legal, okay? That is totally legal. You get to take that piece of paper into the exam with you, right? So if you're super confident, oh, I got that one, okay, I remember this one, okay. But I would go around jotting down arguments, right? So one side of the paper could be just, okay, here's all the different proofs, so I want to make sure I don't forget, right? And then the other side would be, here's all the different calculations and definitions and stuff like that. And by the way, you'll see that you should go through all of the previous exams, right? By the way, this is not a time to not bother to look at the previous exams, right? Because I repeat problems sometimes. All right, so this is extremely fair what I'm doing, right? Competing with myself, right? Because all my best problems, like, oh, I need another problem. It's like hard to come up. It's not like I like to repeat. It's not the idea. It's just that it's hard to think up new problems that are perfect because it's really easy to think up 45-minute problems that are new, right? It's very hard to think up really cool, clever problems that you can do in 10 minutes and 15 minutes that are new. Okay, that's super hard. So you're going to have a huge advantage if you look at all the previous problems. Know them, study them, and then it makes preparing for this test actually just a matter of putting in the time, right? And so make sure you allocate time to go through all the exams and then to make your review sheet and to review everything and then get to the point where you're like, this is stupid, I know it. For me to study anymore would be a waste of my time. I don't know if that will ever happen quite, but that's the goal, to get to that point. And then you feel really good about it, like, okay, come on, I know this stuff. Other questions people want? We got 10 minutes left if you want to do another problem, yeah.
Could you talk about the intuition of why the T prime in the finite frame?
Why the what?
The tangent vector, the derivative of the tangent vector.
Yep.
Is not already unit, even though the tangent vector is unit. I mean, the math works hard, but I don't see figure an intuition how when you bend something that's unit, you get something non-unit.
Oh, okay, you're talking about curves?
Yeah, curves.
Oh, okay, so let's see here. Where should we do this? Right here, maybe? Yes. So this is, again, by the way, that Frenet frame stuff is on there. We haven't talked about it in a while, but of course it's all included. And so you're talking about curves, and you're referring to the fact that we have these Frenet frame formulas, right? Let's just review that real quick. We have T, N, and B, right? And then we can talk about their derivatives. And then, what are the definitions of these things? Let's see here. I have a curve here, parametrized by arc length. Then the velocity of the curve. We're gonna say it's parametrized by arc length, so it's unit speed. Then this curve here is t. This is equal to beta prime of s, and that's beta of s right there. And then you simply say, okay, well, what's beta double prime of s, right? Well, that's going to be some curve in this direction. Now, it doesn't have to be arc length. This one has to be length 1, right? 1, right? This one doesn't. Why? Because we're assuming that the length, the speed, right? We're assuming this equals 1. That's an assumption, right? But we didn't assume anything about beta double prime of s, nor can we actually, right? I mean, we chose a parameterization to where it goes at speed 1, and then there's no control on what this beta double prime of s is. So this is, let's call this vector right here beta double prime of s. And it's some fraction of a unit direction curve here. That unit direction curve we would call n, right? And so what we'll do is we'll say, well, beta double prime of s, whatever that length is, we're calling that kappa, and then whatever the direction is, we'll call n, right? So remember, a vector is a direction combined with a magnitude. So you can always take a unit vector and multiply it by some length. But by the way, but t is beta prime of s, so this also equals t prime of s, right? And so t prime of s is equal to kappa times n by construction, by definition. And then we were like, so we have t defined, we have n defined, and then what you do is you just take the cross product, whoops, and you define this binormal vector. B is defined to be t cross n, I think. Did I get the order correct? So t cross n is going to be going into the board here. And so this is b of s, and that has length 1 as well. These things are all perpendicular. Y. Now why is the first one perpendicular? Well, it's that whole trick, right? T dot t equals 1. Take DDS of both sides, and so t prime is always perpendicular to t, right? And so this is true by construction. Then there was this trick that if you look at all the coefficients here, look at the t coefficient, the n coefficient, and the b coefficient, right? And then t, n, and b up here. And this has t, n, and b also, but they have 0 coefficients there. Then these coefficients all have to be antisymmetric. Why is that? Because if you take any two, like n and b, right? N dot b is equal to 0. Now n dot n equals 1, but then what's true is if I take DDS of both sides, it's always any two of these, even when they're the same, that will be 0, because the derivative of 0 and 1 are both 0. And so then this tells me that n prime of s dot b plus n dot b prime of s, that adds up to 0. But then remember, t, n, and b are by construction, right? They're all unit length orthonormal. They form an orthonormal frame. And so this right here is just telling me the b coefficient of n prime. In other words, it's telling me what this quantity is, the thing that goes in front of the b. And this right here is telling me the n coefficient of b prime, which is this. And so if I look at this diagonal here, right, it's antisymmetric. And in particular, it goes 0 along the diagonal, so you're going to get 0 there, and a 0 here, 0 along the diagonals, because these are antisymmetric coefficients sort of along that diagonal. Antisymmetric matrix has 0 on the diagonals, because when you flip it, they don't move, but it changes by sign. And this is all explained in the book, which means that if that's a kappa there, it must be a negative kappa here, right? If that's a 0 here, it must be a 0 here, right? This is antisymmetric, so that's 0 and 0. And then it only leaves 2 last terms, and you can't actually say anything about them. And so you say, okay, well, whatever this is, call it plus. Is this plus here or minus t? I think plus the torsion, right? And then therefore this must be minus the torsion, right? And there's your Finet formulas. A little more than you asked for, but there you go. So make sure you know all that stuff. And
What sorts of things do we know about torsion when it's constant versus 0 versus neither of those?
I mean, one thing to understand is that this kappa is a second degree quantity, right? It's the length of beta double prime of s, right? There's 2 derivatives of beta. The torsion is the formula for it has 3 derivatives of beta in it. And so I would say the main thing so that's third order, as opposed to second order. And so maybe here's I think this is a true statement. To first order, every curve is approximated by its tangent curve. Like, that's not a bad approximation, right? I can take any curve and approximate it by a straight line, right? That's only looking at beta prime of s, that vector there, right? And saying, okay, make a straight line. It's a pretty good approximation. What if you want to do a second order approximation? Well, instead of approximating it by a line, we could approximate it by a circle, right? That matches up there, right? Okay, well then I need to, what circle are you going to do? Well, how about the circle that's tangent at that point, but also has the same curvature at that point, right? So now that's a pretty good approximation. So the second order, so the first order a curve is a line. The second order you can approximate it with a circle. And then the third order, that's where torsion comes in, we approximate it with a spiral. Okay, so I would I was thinking of it that way. So like, what is torsion? The sort of simplest example would be sort of that spiral, right? You have constant curvature, constant torsion, and I would think of that spiral.
I feel like the other way that I think of it is if curvature is like how out of line it is, torsion is kind of like how out of plane it is.
Uh-huh.
Which is why if torsion is equal to 0, then it always stays in a plane. It's a planar curve.
Yep, that's true as well. Yeah, it's sort of, by the way, which is also, like, what is a spiral? It's a circle that gets out of a plane, right? Yeah.
So could you say that the torsion is never negative?
No. No, I don't think there's any, torsion could be positive or negative. I think the kappa has to always be non-negative. And really, we tend to assume it's positive for, because if it's not positive, then if it's 0, is beta double prime is 0, then this n is not defined. So technically, the Frenet frame formulas all assume that kappa needs to be positive for this all to make sense. But the definition of kappa being the length of beta double prime, that makes it greater than equal to 0. But the torsion could be positive or negative, depending on whether or not you're spiraling up or spiraling down, I guess.
So you could choose any orientation to be positive, right? So you could always choose.
I mean, there's a formula. We've chosen the formula based on when I said it's at a plus or a minus, right? So that defines it, right?
Mhm.
And then there are formulas in the book. Yeah.
Yeah, I think the sign is like the handedness of spine.
Okay.
Yeah, that's right.
Sounds good. I don't remember. Like I couldn't tell you like which one it is which. I have to
I mean, like, if
compute.
you have a right-handed corkscrew up and a right-handed corkscrew down, it's the same shape. But the left-handed corkscrew is a different shape.
Well, it depends on when you start going forward or backwards, right? You got to check the signs of things, right? So
Yeah.
the kappa doesn't change,
Yeah.
but I'm not quite as confident about the torsion because it's a third derivative thing as opposed to a second derivative thing.
I think the idea is it's supposed to be a geometric, and like it's not supposed to depend on like the parameterization of the curve.
I think it does.
Well,
If you put a
it does.
negative t in your parameterization instead of t, your torsion inverts.
Yeah, I would kind of guess that too. But what's the formula? Can you want to read it out of the book? What's the formula for torsion in terms of beta double prime, beta and stuff like that?
It's negative n dot b prime.
It's what?
Negative n dot b prime. There's a couple.
Okay. So okay, that already settles it because n and b won't. T. Okay, actually t changes sign. I don't know. You might be right. Okay, I'm saying I have to check the formula, right? Because when you go the opposite direction, by the way, t goes in the opposite direction, right?
Yeah.
So it flips sign,
I
which
guess-
which means that n does not change sign, but then b does. So b and t both change sign. B and t, but then but then you have a derivative of s here. So I think you're right. Actually, it doesn't flip. So I think the torsion is, if you go like this or go like that, I think the torsion and the kappa are the same. I think you're right. Yeah. Yeah. All right. But good. That's a good test question. Thank you. I'm going to consider that one.